Hello everyone, my name is Mahnaz, and in this video we will share a summary of my PhD presentation titled Analysis of the Interaction of Stress Fields in Zones with Non-Parallel Structures, a case study of Makran-Sistan. Let's get started. Let me explain the definition and problem statement of my research. When structures with non-uniform geometries are placed adjacent to each other, they significantly influence evolutionary and tectonic process. These zones, when positioned in stress fields, result in the distribution of stress fields across up to a structural zone, which directly affects their strain behavior. For example, in Iran, two significant tectonic zones, the Sistan structural zone with a general north-south trend and Makran structural zone with a general east-west trend, exhibit semi-perpendicular geometries. Both of these zones are affected by a stress regime caused by subduction of Oman and ocean crust under the continental crust of Iran. The purpose of this research is to investigate the current distribution of stress field in these zones, interaction of their geometry, and resulting strain fields. This is done using previous research findings, GPS data, focal mechanisms of earthquakes, and pit survey. Now let's move on to the research question. The first question is, how do earthquake mechanisms differ between the tectonic zones of Sistan and Makran? 2. The second question is, what variable govern the changes in the non-tectonic data such as geodetic, geological, and seismic moments in non-parallel structural zone? 3. Which variables can be used to investigate the effects of structural anisotropy on the evolution of transversional and comparational zones? Next. Let's look at the hypothesis of this research. The first hypothesis states that the variation in strain rate, convergence, distribution of the formation and structural pattern is influenced by geometry of a structure relative to the direction of tectonic stress. The second suggests that Norwegian quaternary structure in Makran predominantly exhibit shortening, while those in Sistan primarily shows a strike slip motion. Finally, the third hypothesis is that the geodetic and seismic moment rates are higher in Makran compared to the Sistan, whereas geological moment rate is higher in Sistan than in Makran. Research objectives: analysis of stress field interactions, identification of crustal deformation patterns, evaluation of fault slip rate and moment rates, and seismic potential and earthquake hazard in these two zones. Let's go over the main topics covered in this research. 1. Case study, introducing the study area, tectonic setting, remote sensing, field survey, geology moment, seismic moment, geodetic moment, and discussion and conclusion. Case study, as we said in previous slide, we are gonna study Sistan and Makran, which are located in south and eastern of Iran. Tectonic setting. Sistan structural zone located in eastern Iran between the Nevan and Harirut faults. These zones stretches over 700 kilometers with a north-south trend. Makran is one of the largest subduction zones in the world, located in the southeastern Iran. It stretches about 1,000 kilometers and is bounded by Minop Fault to the west, the Chama National Fault to the east, the Jasmurian Basin to the north, and the Oman Sea coastline to the south. In this slide, I present a brief overview of previous study on fault slip rate. In 2022, Liu and colleagues used high-resolution topographic data and radiocarbon dating to estimate the slip rates of Lahujan fault. Their method involved 3D fault offset and Monte Carlo analysis, resulting in a slip rate of approximately 4.4 to 4.8 millimeter per year. In 2019, Go and colleagues focused on 3D modeling, deformation and stress analysis, and parameter evolution to study fault interactions. The results show that the central segment of Lahujan fault experiences uniform deformation, while the slip rates decrease toward the fault tips. In 2020, Vanjo and colleagues used GPS data for estimating a slip rate of Geological fault 1.2 minus plus 0.8 millimeter per year. In 2023, Qadimi and colleagues used 2D finite elements modeling to study the Makran subduction zone. Their findings indicate a shortening rate of 16.6 to 22.5 millimeters per year. In 2015, Khodaverdian and colleagues using the same 2D finite element modeling, they calculated slip rate of 1.6 millimeter per year for Zahedan fault. In 2014, Walkersdorf and colleagues used the GPS data to measure a slip rate for the East Lut fault and West Lut fault. In 2010, Walker and colleagues used satellite images and topographic map and also field survey to calculate a slip rate for gold fault. The result shows the slip rate for this fault is 3.8 minus plus 0.7 millimeter per year. In this slide, I briefly review previous study on B-value, which formed the basis of this research. Weiss and colleagues in 1997 and Wimmer and Weiss in 1997 studied the B-value, and the results show that low B-value, less than 1, indicate high stress regions typically associated with strike slip or reverse faulting. In 2013, Jafari studied the B-value in Persian Plateau. Their findings suggest B-value below 1 indicates high stress linked to strike slip and reverse fault. B-value around 1 reflects a balanced energy distribution. B-value greater than 1 indicate low stress, often associated with extensional zones. In 2011, Ronnie and colleagues studied the B-value in Makran zone, and the results show that Eastern Makran has a higher stress and decreasing B-value. indicating the stress accommodation in this. This slide explains the use of the remote sensing in this research. We use Landsat and satellite images to identify and map faults, as shown in the map on the right. Additionally, these methods help determine precise locations for field stations to collect accurate fault geometry data. And now you see field stations. I combine geological maps for fault mapping and determining right unit ages. The map on the right shows the results. I conducted 89 structure measurement stations over 20 days, covering different parts of Makran zone. Western Makran along the Dalapan fault. Southwestern Makran focused on Geodetic and Geodic fault in the central of Makran around the Fanuch. In the central of Makran, Iranshah, Niksha, Qasrqand, Rask, Saravan, Suran, and Sirkan, and also in north part of northeastern of Makran around Ghost Fault. Um, 161 stations were completed over 25 days in Sansucho zone, in Gazik, Ahangaran, Shohrat area, and also in Bijan city in the south and north eastern of Bijan, and also around Zabul and Cholvak area, between Birjan and Sepidabe area, and then in Sepidabe area, and then between Sepidabe and Zahedan city, and then between Zahedan and Khash area, in this slide, the methodology is presented as a combination of remote sensing and field study. Remote sensing was used to measure vertical and horizontal displacement of faults. Field study focused on determining the geometry characteristics of faults. Finally, both methods were combined to calculate the net slip of faults. In this slide, I show how the slip rate was calculated along the Lojan fault using a trigonometric method. Horizontal displacement on the left, the topographic map shows control line shifts used to measure apparent horizontal displacement, vertical displacement. On the right, an elevation profile was used to calculate vertical displacement. Finally, the true horizontal displacement was calculated using both values and the trigonometric formula. This slide explains the field study methodology. It involves data collection and observation directly in the field, where geological features are carefully analyzed and recorded to gather accurate information about the faults and rock informations. Due to time limits, we select 4 out of the 254 stations for detailed analysis. The table summarizes the K-fault parameters including strike, deep, break, length, and sleep rate. The photos shows field observation, highlighted the fault trace and step fault features which were used for geometric and kinematic analysis. Dodge fault located in Ohangaron region. The fault runs NWSE and it's about 10-kilometer line. Its mechanism is reverse sinistral. Evidence of activity includes displaced rock units and displacement waterway. The maximum horizontal displacement in waterway along this fault is 533 meters, which shows the fault has been active during different geological periods. This slide focuses on the Hormuz fault in the Sefid-Abe area. The fault runs NWSE and is about 11.5 kilometer long. It is nearly perpendicular to the Sefid-Abe fault. Its mechanism is sinistral reverse. The fault has displaced 510 meters of Cretaceous rocks, and its slip rate is calculated at 2.1 millimeter per year. This slide highlighted the Zahedan fault, one of the most active faults in eastern Iran. It is 216 kilometer long, trending NWSE with a right lateral mechanism. The fault has displaced 2.588 kilometers of Eocene rock units, showing its high tectonic activity over geological periods. This slide focuses on Gasregan fault, one of the major faults in the Makran region. The fault is over 200 kilometer long, trending EW with a dip to the north. It acts as a tectonic boundary, divided the Makran region into inner Makran and outer Makran. Its mechanism is reverse sinistral, indicating horizontal and vertical displacement. The Landsat image of Gasregan fault shows waterway displacements. The maximum horizontal displacement along this fault is 1.72 kilometers. Geological moment. The geological moment rates reflect the potential of faults to generate seismic activity. We calculate geological moment from this formula, and then we draw geological moments rate map in ArcGIS software. As legend shows, pink and red faults have the highest geological moment rate. And in this slide, you see sleep rate and geological moment and other parameters for. This slide summarizes the sleep rates and geological moment rates in Sistan and Makran. In Sistan, the Sefid-Abe fault has a sleep rate of 1.0 millimeter per year, and the Zahedan fault has a sleep rate of 1.53 millimeter per year. The total geological moment rate in this zone is approximately 2.76 times 10 to the 17 Newton meters per year. In Makran, the Kasragan fault has a slip rate of 3.75 millimeter per year, and the Sarabon fault has a slip rate of 5.82 millimeter per year. The total geological moment rate in this zone is about 1.09 times 10 to the 18 Newton meter per year. The slip rate and geological moment rate are higher in Makran compared to the Sistan, indicating greater tectonic activity in Makran. This slide explains using GPS to track cross movement and study tectonic activity. This slide shows how we divided the study area using the linear triangulation to study cross movement. The red line on the map connects GPS stations. The black lines show the direction and speed of the cross movement. Longer lines means faster movement. The table includes the location of each station, movement speed to east-west and north-south, errors in the measurements, and solution. This slide shows a mathematical equation used to study how the Earth's crust moves and deforms. The composition of movement on the left side of the equation is breakdown motion into parts showing how the crust moves east or north. The formation matrix in the middle of the equation, the matrix describes how much the speed of movement changes in the different directions and coordinate differences. On the right side, the delta E and delta N values represent small changes in the position which are used for prices calculations. This slide explains how we use equation 3 to calculate changes in the speed and movement of Earth's crust. On the left side, we have known speeds at the triangle's corners. In the middle, coefficients from the triangle's coordinates are used. On the right side, we calculate unknown value, the speed at the center, and the velocity gradients. And from this equation, we are able to calculate T, a strain tensor, and a rotation matrix R. This table shows the result of a strain calculation for different triangles number and corners. Strain rate tensor components, columns T11, T12, T22, and shear strain rate and total strain. This slide shows the regions with the highest geodetic strain rates in Sistan and Makran. The highest strain rates are observed in triangles 12, 42, 41, 16, and 5 located near the Oman Sea. These rates result from the Makran subduction zone and collision of Arabian and Eurasia plates. SR's direction is primarily an ESW, consists with the Arabian plate moving toward Iran. In Sistan zone, highest strain rates occur in triangles like 35, 6, 30, and 29. Compression rate decreased gradually from north to south in the Sistan suture zone. In Makran, strain rates are higher and influenced by subduction and plate collisions. In Sistan, strain rates are lower and mainly controlled by local faults and internal tectonic structures. This slide explains the geodetic rotation speed in the Makran-Sistan. In Makran, the highest rotation rates are in triangle 12, 5, 37, 27, and 14, Western Makran. In Western Makran, the rotation is anti-clockwise caused by the collision of Arabian and Eurasia plates. Eastern Makran shows a slower clockwise rotation due to Indian Eurasia plate collision. Sistan region, highest rotation rates are in triangle 31, 32, 29, 35, and 23. In Sistan, rotation shifts gradually from anti-clockwise in the north to clockwise in the south, such as triangle 44. The geodetic moment rate is higher in Makran compared to Sistan due to several reasons. Makran. The nearly perpendicular subduction to the Makran leads to significant shortening. The fleshy sediments in this area are soft and form easily under pressure. Sistan. The hard and rigid crust in Sistan resist shortening, so tectonic energy is released through other mechanisms. Most of the stress is released through the right lateral strike slip, line measure fault like Nehbandon and Neuband faults. Seismic moment rate in Makran is higher than in Sistan due to the seismic moment rate in Makran is higher than in Sistan due to high seismic moment from larger energy release, active reverse faults, storing and releasing energy, active tectonic setting with subduction zones. The orientation of maximum stress in our study aligns with the finding of Zoback 1992 as presented in the World Stress Map project, and also the orientation of maximum stress in our study align with the finding of Ahtop and Oostdorp regarding regional tectonic regimes. Also, we compared b-value, our b-value result with previous studies like Jafari and Ahtop and Oostdorp and Ronnie et al. To 211. The seismic moment rate in Makran is higher than in Sistan due to high seismic moment from larger energy release, active reverse faults, storing and releasing energy, active tectonic setting with subduction zones. The orientation of maximum stress in our study aligns with the finding of Zoback 1992 as presented in the World Stress Map project, and also the orientation of maximum stress in our study align with the finding of Ahtop and Oostdorp regarding regional tectonic regimes. Our result compared with previous study such as Jafari 2013, Ahtop 2022, Rani 2011. Conclusion. The slip rate of faults in Makran is higher than that in Sistan. The geological moment rate in Makran is higher than that in Sistan. The geodetic moment rate in Makran is higher than that in Sistan. The seismic moment rate in Makran is higher than that in Sistan. The B value in Eastern Makran is lower than that in its western part. The B value in the northern and southern part is lower than that in the middle. Thank you so much for watching this video. Goodbye.